Hi everyone, we're going to continue our discussion on stereochemistry, this time focusing on a concept called optical activity and how we can use optical activity to determine enantiomeric excess in a mixture of compounds. So recall that enantiomers are non-superimposable mirror images of each other. So for example, here is R2-butanol and here is S2-butanol. So the only difference between these molecules is that they are mirror images, which means that they exhibit identical physical properties. So properties like boiling point and melting point will be identical across these two enantiomers, which makes sense. The only difference here is they're mirror images, but they would have exactly the same kind of intermolecular forces that dictate these types of physical properties. However, enantiomers exhibit different behaviors when exposed to what we call plane-polarized light. So what we're going to do is explain what plane-polarized light is and how it is affected by running a plane-polarized light through a sample of a pure enantiomer. Okay, so in our discussion of plane-polarized light, the first thing I want you to do is consider a light source. This light source can come from any type of element, but this time, especially when it comes to this kind of experimentation, we're going to consider a light source from sodium. It's going to travel through space in all planes. So you can think about it as all planes around a circle. You're going to imagine that light just traveling in a straight line across all planes. And then now imagine if you take that light and you pass it through a very thin slit. So this is what we've denoted in this particular blue diagram. And that slit opening is just enough space for light to travel in one of the planes that you were previously traversing through. And we call this a polarizer. So the idea is that you're going to cut off light in every other plane except for one. So now imagine that light traveling through that particular slit. What you should end up with is this particular result where what's coming out of that polarizer is simply light in only one plane. And so we're going to call this plane polarized light. Okay, so now we're going to take this plane polarized light and we're going to pass it through a sample of pure S2-butanol. So what is going to happen is, as the light travels through that sample of pure S2-butanol, what actually goes on is a rotation of that light, and it actually rotates in a specific direction. For pure S2-butanol, it's actually going to rotate in a clockwise direction. So notice that rotation going on here. Okay, and that clockwise rotation, we call it the positive rotation. So the plane is polarized light is rotating clockwise. And this, we could have only determined this from experiment. So there was nothing about that structure of S2-butanol that would make us predict this particular experimental observation. However, because it rotates plane polarized light clockwise, we call S2-butanol dextrorotatory. So dextrorotatory will be a compound that when you place that compound under plane polarized light, it would rotate that plane polarized light clockwise. We also can notate this experimental observation within the name of 2-butanol. So we can put that plus sign in front of its name and just call it plus 2-butanol, and that would tell us that this particular stereoisomer of 2-butanol is dextrorotatory. In other words, it rotates plane polarized light clockwise. And any compound that rotates plane polarized light in any way is considered optically active. So that is what we call optical activity. Okay, so now let's consider plane polarized light passed through a sample of R2-butanol. So now the enantiomer of S2-butanol. So once again, we pass that plane polarized light through a sample of R2-butanol. Over time, what's going to happen here is that plane polarized light is going to rotate once again. However, it's going to rotate in the opposite direction as S2-butanol. So notice that this time it's rotating counterclockwise. This counterclockwise rotation is also called negative rotation. So that's why we have the negative notation over here. And any compound that rotates plane polarized light in a counterclockwise direction or negative rotation is called levorotatory. So levorotatory will be the counterclockwise rotation. And once again, there's no way we could have determined the counterclockwise rotation of plane polarized light by R2-butanol from its structure. We had to have done this experimentally to know that R2-butanol rotates plane polarized light in a levorotatory manner. And so the notation that we can then include into the name of R2-butanol is by putting a negative sign in front of that particular sample. And so when we say negative in parentheses and then 2-butanol, we're just saying that this particular stereoisomer 2-butanol rotates plane polarized light in a negative direction or in a counterclockwise direction. And once again, because R2-butanol, it has the ability to actually rotate plane polarized light, we call R2-butanol optically active. And just to drive home this point, in case you haven't noticed this from this particular scene, all chiral molecules are optically active. So if you put a pure sample of a chiral molecule within plane polarized light, it will absolutely rotate plane polarized light in some direction, whether it's clockwise or counterclockwise. Okay, so now let's talk about how to quantify the optical activity of a particular enantiomer, a particular chiral molecule. But before we move on, it is worth stating, like if you think about the last scene, enantiomers will rotate plane polarized light in equal amounts. Once again, they're just mirror images. However, they will rotate plane polarized light in opposite directions. And this is really key because this is actually how we can experimentally determine which enantiomer we potentially would have in a particular sample. And the degree to which that particular chiral sample will rotate plane polarized light, in other words, the observed rotation, which we denote as alpha, the alpha symbol, is dependent on two things. One is the sample concentration, so how much of that particular chiral molecule you have in the sample would dictate the extent in which the rotation will occur. It would also depend on the distance the light would travel through the solution. So the longer the distance, the more the light will rotate, or the more magnitude of rotation you would observe. This is also called path length. So the observed rotation is dependent on both the concentration and the path length. So here is the equation for observed rotation. So the observed rotation is equal to a constant we're going to call alpha D20 times the sample concentration times the path length. The symbol D is just denoting that the source of our light is from sodium, and that's a typical light source for our experimentation of optical activity. And then that 20 is just denoting the temperature in which your optical activity experiment was taken. And so we usually would take this particular sample and run it through a light source at 20 degrees Celsius. Therefore, if you rearrange your equation, alpha D20 is equal to the observed rotation over the concentration of your sample times the path length. So while alpha is called the observed rotation, which is dependent on sample concentration and the path length, alpha D20 is called the specific rotation, and that is independent of sample concentration and distance. We've been able to reduce both of those down to 1 on both regards. So this is really important when you're trying to compare across different samples. You want to have a constant that does not depend on concentration or the distance with the light travels, because that means every experiment is going to give you a very different number. So the alpha D20 is actually a very important number that helps us compare across different samples. And just for your information, the unit of concentration that we would use in this particular equation is in grams per milliliters, and the path length is in decimeters. So yeah, the units do not actually cancel out per se. And we usually report alpha D20 or the specific rotation without its units. So even though we make sure that the concentration is in grams per milliliters and the length is in decimeters, alpha D20, when we report it, we just report it as if it were unitless. Okay, so now going back to our sample of S2-butanol versus R2-butanol, the alpha D20 for S2-butanol is positive 13.9. Remember that positive, it means it's dextrorotatory, or it rotates plane-polarized light clockwise. And then R2-butanol, on the other hand, is the exact same magnitude as S2-butanol when it comes to the alpha D20. However, it is negative 13.9, which is saying that it's rotating plane polarized light in the opposite direction, which is your counterclockwise direction. Okay? So now we're going to see how we can use this experimentation of plane polarized light to talk about enantiomeric excess. So let's think about some concepts first of all. If we have a pure sample of a single enantiomer, we call that pure sample optically pure. If you have a sample containing an equal amount of both enantiomers, we call that sample a racemic mixture. And racemic mixtures are optically inactive. So they do not rotate plane polarized light in any direction. Now, a sample containing an unequal amount of both enantiomers, so one of those enantiomers will have a higher concentration than the other, will still be optically active. It will not be optically pure, and so that rotation will be diminished. So there'll be a diminished rotation, or it'll be diminished optical activity. Okay, so now let's illustrate this concept in an actual example. So let's think about this as if it were a spectrum. On the left-hand side, we have pure R2-butanol, and on the left-hand side, we have pure S2-butanol. Okay, so we go through that spectrum. So if you had pure R2-butanol, so assuming 1 gram per milliliter of your R2-butanol and a path length of 1 decimeter, you should have an observed rotation of negative 13.9. On the other side, if you have pure S2-butanol, the observed rotation when you have 1 gram per milliliter of that sample in a 1 decimeter path length will be positive 13.9. In the middle of this spectrum, where you have an equal amount of R and S in your sample, so that's your racemic mixture, your observed rotation is going to be equal to 0. So there will be no rotating of plane polarized light. This would mean that if you have an unequal amount of both of your enantiomers in a sample and you had more of your S2-butanol than your R2-butanol in your sample, you should get an observed alpha where it's positive value, but it will be less than 13.9. So somewhere in between 0 and 13.9 will be your observed alpha if the S2-butanol is more than your R2-butanol in your sample. And then on the other side, if you had a sample of some combination of R and S and you get an observed alpha that is negative sign, so somewhere between 0 and negative 13.9, that means that you have a sample in which you have more R2-butanol in your sample than S2-butanol in your sample. So let's say you actually took a sample of S and R2-butanol, and you found that the observed rotation is equal to positive 4.7. This would mean that you have an excess of S2-butanol over R2-butanol in that mixture because it's a positive value between 0 and 13.9. But by how much? Well, there's a way to figure out that question, and that is figured out by what we call enantiomeric excess, which is your percent EE, which is calculated by if you take the absolute value of your observed rotation, divide that by the absolute value of the rotation of the pure enantiomer, so the specific rotation of the pure enantiomer, and multiply that by 100. So the solution to the above problem of a sample of S and R2-butanol where the observed alpha is positive 4.7, and then you get an enantiomeric excess at 34%, which means you have 34% more S2-butanol in this mixture. And so in this video, what we have learned is optical activity, how to use experimentation to determine optical activity. We've defined this concept of alpha D20 as a way to both show the purity of a particular enantiomeric sample, as well as calculate enantiomeric excess. Okay, and that's it for the video. Thank you so much for watching, and I will see you in class.